Jai Hind everyone. I am Ankita Sharma. I work here in Ajay Kumar Garg Engineering College as an assistant professor in ECE department. So today we are here to cover our first topic, that is complex topic, timing diagram of 8085, and it comes under the series scheme of BEC 502 of subject microprocessor and microcontroller in AKTU. So first of all, what is a timing diagram? So timing diagram is generally a graphical representation of clock cycle and duration that represents clock cycle and duration. The things which microprocessor do, like microprocessor first of all fetches, then decodes and then executes. So these three cycles are covered in the timing diagram. We can see how the things are copied and how the things are happening at the back end. So first of all, before further going to the timing diagram, I just want to tell you something about the machine cycle. Machine cycles. So machine cycles is generally the time required by the microprocessor to complete one task. Suppose the time required by the microprocessor to fetch something, and what we will be fetching? We will be fetching, microprocessor will be fetching the opcode first, and after that the operands will be fetched. So first of all, the very first machine cycle will be of our opcode fetch. That is the first machine cycle. There are 5 machine cycles total. 5 machine cycles will be there. So first is our opcode fetch. Second will be our, so microprocessor has fetched the opcode. After that, what are the operands? Are they some registers or the data or the memory location? For that, the microprocessor will be dealing either from some peripheral or from the memory. So for that, there will be 2 machine cycles related to the memory, that is known as MEM. Here is memory, memory read, memory write. So these 2 will be dealing with the memory only. So 3 machine cycles are opcode fetch, memory read, memory write. Except the memory, the microprocessor deals with the input output peripherals as well. So for that, I will be writing that input output, that is IO read, and fifth will be IOW, that is input output write. So these machine cycles will be there. These are 5 different machine cycles that will be covering in the 8085. So the prime requirement for the machine cycle or for some instruction to be read, the very first thing will be our opcode fetch. The microprocessor will be fetching the opcode. What the function is there? For example, I have to move from register B to register C. The opcode for this will be move B, C. I have to copy from register C to B. The contents of register C will be copied to B. For this, there will be some machine code that is already predefined in the microprocessor, and for suppose for move B, C, the machine code is 78. Now the 78 machine code will be fetched. This opcode will be fetched by the microprocessor, and for that we will be needing some T states. T states are time states. These are some time slots that we will be covering here, how these time slots are defined and how this opcode is fetched, how next operand will be fetched, and so on, and how a instruction is read at the part of microprocessor. For that, it is a graphical representation of the process with respect to time. We will be dealing with the time, and the timing diagram further represents the clock cycle. What is the clock cycle and what is the duration, what is the delay, the content of the address bus, data bus both, and what are the status signals of this particular instruction, and what are the time of operation, the type of operation, are we reading something, are we writing something, all these things, and status signals also. Status signals, we are having 2 status signals here, that is S0 and S1. For machine cycles, if I talk about, machine cycle is generally the time required by the microprocessor to complete some operation, and that operation will be accessing from the memory device or the input output device. So the time required by the microprocessor to fetch that instruction from the microprocessor or the IO device, and the instruction cycle is completely fetching this thing and execution. So it will be fetch plus execution of an instruction is our instruction cycle. So instruction cycle completes with the fetching and the execution. Decode is the hidden thing here. And T state is generally, each clock cycle is called a T state. For example, opcode fetch is an we can say a step to fetch the opcode. So here T state is our clock cycle. Every machine cycle will be having some T states. For example, opcode fetch will be having 4 T states. Memory read, memory write will be having 3 T states. Similarly, input output read, that is IOR and IOW, input output write, these all will be having 3 T states. Only the opcode fetch is the only machine cycle that will be requiring only 4 T states. Other than that, all the 4 machine cycles will be requiring 3 T states. That we have to remember, that the 5 machine cycles will be having different T states. So this is the T state. As we all know, this is a clock. The clock have 2 things, 2 edges are there in a clock. One is called positive edge or a rising edge, or falling edge or a negative edge. So rising edge will be from 0 to 1 upwards, that is why it is called as rising edge, and falling edge will be from 1 to 0, from positive to negative. That is why it is called as negative edge. So this transition, when one cycle is completed, like this one, if I talk about a clock, this completes 1 T state. This is a T state. This is 1 T state. This is 1 T state, and in microprocessor there are number of T states for fetch and execute. Suppose here fetch, I just told you, like in opcode fetch we require 4 T states. So here are 4 T states for opcode fetch and 3 T states for the execution. For execution we will be needing, we'll need memory read, memory write, input output read or input output write. That is execution part. So total instruction cycle will be minimum of 7 T states. So these are the following buses and control signals that must be shown in a timing diagram. Timing diagram generally is consists of different things, like the clock will be there. After having the clock, the microprocessor will be reading some data from some particular address, and for that address should be there in the address bus, and address bus is of 2 types, as we all know, lower address bus and higher order address bus. So higher order address bus is A15 to A8 and lower address will be our A7 to A0. Here AD7 to AD0 is written as it is a multiplexed or time shared. It is shared by data and address both. That is why. So ALE is there. ALE is address latch enable. If this pin is 1 and if this pin is 0, there are 2 possibilities. So when the ALE is 1, this time shared or multiplexed bus will be carrying only address. It will be carrying address. And now when the ALE is having 0, then it will be calling only data at that time. Next is our read signal. Read signal is an active low signal, that is why a bar is there. Write signal is also an active low signal, and here it is IO/M bar. IO/M bar is input, output and memory. As we all know, microprocessor will be reading the data either from the memory or from the input output. So if the microprocessor have to read the data from the input output, then this pin will be 1. If 1 is there, that means input output will be giving our data, and if the value is 0, as memory is an active low signal, when 0 will be there, 0 will be complemented, and complemented means 1, and this pin will be 0, this will not work. So when IO/memory bar is 1, microprocessor will deal with the input output, and when the pin IO/M bar is 0, the microprocessor will pick the data, will read the data, or will write the data at the memory, will be dealing with the memory only. This is the main thing we all have to remember while covering our timing diagrams. So what is opcode fetch? Opcode fetch that we have discussed just now. The microprocessor requires some instructions to perform some particular action. For example, microprocessor have to do addition. For addition, it will be requiring some instructions regarding addition, and that instruction will be forwarded to the ALU, and ALU will further identify which two registers, which two numbers are to be added, and so on. So that is why the microprocessor will utilize the opcode, and opcode is a part of an instruction, and after opcode the operand will be there. So we can also say if an instruction is there, so instruction will be having two parts. The first part is our opcode, that is fetched first, and next part is our operand. Operand is the data or the register on which the instruction is to be performed. So for example, here we are taking an example of a move instruction. The instruction is move A, B. This is the timing diagram. We will learn how to make this timing diagram. I'll explain you the same example with the same example here. Move A, B. B is our B register, which is an 8-bit register. A is our accumulator. It is also an 8-bit register. What we are doing, microprocessor will copy the contents of register B to accumulator. For that, there is some location here. H is signifying the hexadecimal number. H is representing that this 8000 is an hexadecimal number. So 8000 is there, and the corresponding coding, the machine code for move A, B is 78. So what the microprocessor will do, this is 8085 microprocessor, this is memory. The microprocessor will be opcode fetch from the memory. That is why the direction is from memory to microprocessor. The microprocessor is reading the opcode from the memory, and this opcode is given at this particular address 8000H. Now let's start with the example and some examples from this. For example, the first thing was move A, B, move A, B, and the opcode was 78 and address is A000H. First of all, what we have to do, we have to do some vertical lines here. How many T states are required for opcode fetch? That we know. For opcode fetch, I will be needing T states, 4 T states, 4 T. So T1, T2, T3, T4. Now second thing we require for any device to operate is clock. This is one clock, this is second clock, another one, fourth clock. This is our clock. The clock can be drawn like this and like this as well. Both are correct. You can use any two of them. I am using this one, as there is some transition, there is some delay when you just switch on some device, there is slightly delay. So this clock will be just showing that delay so that we can further do. Next thing, If the address is A000H, here it is having higher order address and lower order address. So that means the buses starting from A15 to A8 will be carrying A0, and address bus that is from A7 to A0 will be having the address 00H, hexadecimal numbers. And what about the data bus that is from D7 to D0? The data bus will be carrying the data that is 78, the machine code, the opcode. So 78, it is also a hexadecimal number, or we can simply say 78. Next thing, it will be the opcode. Now, the very first thing a microprocessor requires is the address from where, the address in the memory. This address is of memory. So microprocessor requires some address of that particular memory, and from this address this will be read, 78. So I need higher order address bus, that is A15 to A8. As we can see, there is a slight delay from here. So the microprocessor further will be having a slight delay, as 8 address lines will be having 8 bits, A and 0. There will be some zeros and there will be some ones in there. So that is why 0 and positive pulse 1. So for an address, higher order address, approximately 3 T states are required, and at the last T state, the execution or the decoding part is started. So that is why we can do it like this also. You can completely cover this with the address line, it is also okay, and you can just put it like this, this is also okay. Both are correct. After the address, now what I need? I need lower order address, but there is a condition for the lower order address, as this and this, these both address and data lines are time shared. To select one out of these two address and data bus, I need one signal that was ALE. ALE should be 1 for address and ALE should be 0 for data. For address, I will be selecting ALE as a positive pulse. Suppose I have selected it as a positive pulse, and after that it is negative. I need a positive pulse here, and I got 1, and when the value of ALE is 1, that multiplexed address data bus will be carrying the address. Which address? The lower order address. So lower order address here is this. This is our higher address, and this was our lower address, and this is my data bus. 3 things are there. So for lower address, AD0 to AD7, or we can say AD7 to AD0, it will be more correct. AD7 to AD0. For that, 8-bit data is there, that is 00. Similarly, a slight delay for a positive pulse and a negative pulse. And to transfer the lower order address, approximately 1 T state is required. That's it. That's it. Other than that, the opcode will be given. But for the opcode will be read or write. The microprocessor have to read from the memory. Read from the memory. The microprocessor will read from the memory. That is why our read bar signal will be activated, because microprocessor will read. Now, read bar signal will be there and write signal will also be there. Here address is transferring, read bar signal will be active high, because at this point reading is not done in the microprocessor from the memory, but when we are reading the opcode 78, at that point it will go active low for 1 T state approximately, and at this point of time when this is happening from here, to here, lower order address bus will become a data bus, will act like a data bus, and here our opcode will be transferred. Opcode here is 78. Here it was A0H, here it is 00H. So 00 is in A15 to A8, A7 to A0 is 00, and D7 to D0 is opcode. From here it is reading from this to this part. Next is write. Do I need some write signal? No, I will not be having any write signal. For that, the write signal will be active high all the time. So this is the complete. And one more thing I forgot here, most important thing, input output / memory bar. The microprocessor will be dealing with the memory only here, as the microprocessor is reading the address from the memory, and at this address, this is the memory. At address A000H, 78 was written in the memory. This is memory. So both opcode and the operand are microprocessor is getting from the memory. So that is why I need memory bar, and memory bar is an active low signal. For that, for whole period, for all the t states, the value will be of IOM bar is 0. So this is the complete timing diagram for opcode fetch. Similarly, we can do this for memory read as well. This is the memory read. And one more thing, the number of the instruction given here is move A, B. We have to find out what is the size of this instruction. As we can see, there is only opcode given, and when only opcode is given, it is a 1 byte instruction. This is a 1 byte instruction. So for 1 byte instruction, we need 2 machine cycles. For 2 byte instruction, we will be needing 2 machine cycles, and for 3 byte instruction, we will be needing 3. We will need 3 machine cycles. So next example here is for MVI A, 44H. This is a very important example. MVI A, 45H. Now, what is the size of this instruction? As we can see, MVI A is an opcode, it is of 1 byte, and 45 is a data. 45 is a data that is of 8 bits or 1 byte. So total, this instruction is of 2 bytes. So for 2 bytes, there will be 2 machine cycles. One is for opcode fetch here till T7, and from T6 to T7 it will be memory read. So opcode fetch is exactly same here. Opcode fetch is same. If you see here, this is clock given. This is A15 to A8 given. This is our AD7 to AD0 given. This is ALE given here. This is our read signal, write signal, and input output memory bar. So what is exactly happening here? These 4 T states are same, just like the opcode fetch we have done earlier. This one, these 4 T states, this machine cycle is exactly same. But for memory read, what we are doing? For memory read, suppose the address is A000H and it is carrying MVI A, 45H. So MVI A is having an opcode 3E. So for A000, it will be having the data 3E, and after one increment A001 hexadecimal, it will be 45, which is given here. So we will need 2 memory locations, that means 2 bytes, and 2 bytes means 2 machine cycles. This address and this opcode here will be done by opcode fetch machine cycle. It will need T1 to T4 machine cycles, and A001, this is our memory read machine cycle, and memory read machine cycle need 3 T states. So total number of T states will be 7 T states here, T1 to T7. So till here we have covered in the opcode fetch. What is exactly happening here is, if we see A0, higher order address will be going, lower order address is 0, 1, but for lower order address or data, what will go in the bus, it is decided by the ALE. So this pin is enable 1, address is going. When this ALE is 0 here, ALE is equal to 0 here, ALE is equal to 1 here, then the data, that is 45 is going. But thing is that the 45 is memory read, we have to read, that is why read bar here is 0, write bar is permanently 1, because microprocessor is only reading, not writing. And last but not the least and the most important pin, IO/M bar, input output or memory, from where the microprocessor is carrying. Microprocessor is carrying from the memory. So that is why it is IO/memory is equal to 0. So this is a complete timing diagram for 2 bytes of instruction, and there is an example of 3 byte instruction. Here we will be having 3 machine cycles. As you can see, all the functions are same. Higher order address, higher order address, higher order address is going, lower order, lower order, lower order, opcode, opcode and opcode. ALE is enabled, lower address is going, ALE enabled, lower address going, ALE enabled, lower order address going. When read bar is active, data is going, read bar is active, data is going, read bar is active, data is going. Write signal is completely not active, and memory से deal कर रहे हैं, so that is why it is IO/M bar is equal to 0. So these are the some references for this, and I hope this finds you very well, and this is a very important topic as per the university curriculum. So thank you so much.